Hi there, welcome back. This week we're getting into the cool stuff with TensorFlow. In this lesson, Vincent will show you how to build a multi-layer network, which you've seen before, but now you get to do it in TensorFlow. Next, you'll learn how to use a deep neural network to extract features from images. These types of models are called convolutional networks, or ConvNets. They can be used to detect and recognize objects in pictures with amazing accuracy. Also, AWS credits. You'll each get $100 of credits to use on AWS cloud machines. We've built a lesson to teach you how to use an AWS EC2 instance for training your networks on a GPU. It'll change your life. And finally, we're launching the second project. It's on object recognition. You'll train a convolutional network on a bunch of images from the CIFAR10 dataset. It'll be able to differentiate between frogs and cats and cars and planes. I think you'll find it an interesting challenge. Cheers!
So now you have a small neural network. It's not particularly deep, just 2 layers. You can make it bigger, more complex, by increasing the size of that hidden layer in the middle. But it turns out that increasing this h is not particularly efficient in general. You need to make it very, very big, and then it gets really hard to train. This is where the central idea of deep learning comes into play. Instead, you can also add more layers and make your model deeper. There are lots of good reasons to do that. One is parameter efficiency. You can typically get much more performance with fewer parameters by going deeper rather than wider. Another one is that a lot of natural phenomena that you might be interested in tend to have a hierarchical structure, which deep models naturally capture. If you poke at a model for images, for example, and visualize what the model learns, you'll often find very simple things at the lowest layers, like lines or edges. Once you move up, you tend to see more complicated things like geometric shapes. Go further up, and you start seeing things like objects, faces. This is very powerful because the model structure matches the kind of abstractions that you might expect to see in your data. And as a result, the model has an easier time learning them. Why did we not figure out earlier that deep models were effective? Many reasons, but mostly because deep models only really shine if you have enough data to train them. It's only in recent years that large enough datasets have made their way to the academic world. We'll look at another reason now. We know better today how to train very, very big models using better regularization techniques. There is a general issue when you're doing numerical optimization, which I call the skinny jeans problem. Skinny jeans look great. They fit perfectly, but they're really, really hard to get into. So most people end up wearing jeans that are just a bit too big. It's exactly the same with deep networks. A network that's just the right size for your data is very, very hard to optimize. So in practice, we always train networks that are way too big for our data, and then we try our best to prevent them from overfitting. The first way we prevent overfitting is by looking at the performance on our validation set and stopping to train as soon as we stop improving. It's called early termination, and it's still the best way to prevent your network from over-optimizing on the training set. Another way is to apply regularization. Regularizing means applying artificial constraints on your network that implicitly reduce the number of free parameters, while not making it more difficult to optimize. In the skinny jeans analogy, think stretch pants. They fit just as well, but because they're flexible, they don't make things harder to fit in. The stretch pants of deep learning are called L2 regularization. The idea is to add another term to the loss, which penalizes large weights. It's typically achieved by adding the L2 norm of your weights to the loss multiplied by a small constant. And yes, yet another hyperparameter to tune. Sorry about that. The nice thing about L2 regularization is that it's very, very simple. Because you just add it to your loss, the structure of your network doesn't have to change. You can even compute its derivative by hand. Remember that the L2 norm stands for the sum of the squares of the individual elements in a vector. Which of these formulas gives you the derivative of the L2 norm of a vector? There is another important technique for regularization that only emerged relatively recently and works amazingly well. It also looks insane the first time you see it, so bear with me. It's called dropout. Dropout works like this. Imagine that you have one layer that connects to another layer. The values that go from one layer to the next are often called activations. Now take those activations and randomly, for every example you train your network on, set half of them to 0. Completely randomly, you basically take half of the data that's flowing through your network and just destroy it, and then randomly again. If that doesn't sound crazy to you, then you might qualify to become a student of Geoffrey Hinton, who pioneered the technique. So what happens with dropout? Your network can never rely on any given activation to be present, because they might be squashed at any given moment. So it is forced to learn a redundant representation for everything to make sure that at least some of the information remains. It's like a game of whack-a-mole. One activations get smashed, but there is always one or more that do the same job and that don't get killed. So everything remains fine at the end. Forcing your network to learn redundant representations might sound very inefficient, but in practice it makes things more robust and prevents overfitting. It also makes your network act as if taking the consensus over an ensemble of networks, which is always a good way to improve performance. Dropout is one of the most important techniques to emerge in the last few years. If dropout doesn't work for you, you should probably be using a bigger network. When you evaluate a network that's been trained with dropout, you obviously no longer want this randomness. You want something deterministic. Instead, you're going to want to take the consensus over these redundant models. You get the consensus opinion by averaging the activations. You want YE here to be the average of all the YTs that you got during training. Here's a trick to make sure this expectation holds. During training, not only do you zero out the activations that you drop out, but you also scale the remaining activations by a factor 2. This way, when it comes time to average them during evaluation, you just remove this dropout and scaling operations from your neural net. And the result is an average of these activations that is properly scaled.